I am Krishna Kumar from Krishna's classroom. So we continue with our discussions on the change of basis and the consequences. Let us first consolidate the results that we obtained, especially in a case where we will be using it more frequently. In a special case, we actually made this statement of this theorem. So let me just put it out as a theorem. We have already completed the discussion and the proof of that. So we have the following here. Let me just write this up. We have already proved this result. So let V be an n-dimensional vector space over a field. Let B designating the ordered basis V1, V2, etc. Vn, and B prime designating the ordered basis Vn prime. Be two ordered bases for if P denotes is the n by n matrix with columns Pj J prime with respect to P, then the ordered or the matrix representation of P with respect to B prime equal to P inverse of the matrix representation of P with respect to B alternatively if U is a linear transformation, is an invertible linear invertible operator on V defined by prime for j equal to then P with respect to the basis B prime is equal to this theorem we have already proved. Here of course the special case, it's a special case where we are considering both the domain space and the range space as two. But the general form we have already given, and I don't think because it doesn't come into application very much. So we just keep it as it is, and this form in which we often use it. Now let us look at the examples. Now the first example that we consider is choosing V equal to R2. This is a vector space over R. The dimension of equal to. So we choose two ordered bases. The first ordered base B that we choose is the standard ordered base, namely 1, 0, here. Then in our notation B1 equal to 1, 0, B2 equal to 0. Let B prime be defined by 1, 1, 2, 1. This is again an ordered basis. You can check easily that these two vectors are linearly independent. Therefore, it spans the whole space also. So there are two vectors here which spans the whole space. Therefore, what we take now is that V1 prime in our notation is taken as 1, 1, and V2 prime we take as 2. Now we observe that. So first what we want to do is we want to computation of pi, P. Computation of P. How do we do this? what we do is that we write V1 prime in terms of V1 and V2. Then this is equal to 1 times V1 plus 1 times V2. So also you write V2 prime as 2 times V1 plus 1 times, and then look at the definition of P. Then P turns out to be 1, 2, that means these coefficients become the rows, or in other words, these coefficients become the first row, these coefficients become the second row. So P is this, and P is invertible. P is invertible, and P inverse can be easily computed. This can be computed to be, you can go to the usual process of computation of the inverse of the matrix, or directly work it out. Directly working out is you write V1 in terms of V1 prime and V2 prime. So also V2 in terms of V1 prime and V2 prime, and then you do as you did in the case of P. So that will give you the inverse, because it's going back from V1 prime, V2 prime to V1, V1, V2, that will give you P inverse. So P inverse computes to be this one. You can verify that. So now I think we have obtained we have computed the P. Okay. Now the next stage is, so T is given. TV1 and TV2 equal to 0. That's the definition of this. Because what you are doing is you are prescribing at V1 and at V2 the value of T. Now let us see what is the representation for the matrix representation for T. That's the first step. So the matrix representation for T is then, so to compute of T so this is what we are working. So you write down TV1 equal to 1 times V1 plus and TV2 0 times V1 plus 0 times V2. Therefore, the matrix representation of T with respect to V, these coefficients appear as the first column. So you get 1, 0. Then these coefficients appear as the second column. So that is the matrix representation of T with respect to V. Now we compute matrix representation of B prime. So for that, what one does is this. What is T V prime, V1 prime? What is V1 prime? V1 prime is 1 1. So this is equal to T of what is V1 prime? V1 prime is actually 1 times V1 plus 1 times V2. Therefore, this is equal to P V1. Now T V2 prime, this is equal to T of 2V1 and that's equal to twice V1. Okay. Therefore, we can write T V1 prime is equal to now what we need is we have to write it in terms of V1 and V2 in terms of V1 prime and V2 prime. Okay, so let us do that. So V1 prime, V1 is equal to minus V1 prime plus V2 prime. Okay, that's not something which you can easily verify. Right? Similarly, therefore V2, therefore TV1 prime similarly TV2 equal to V1. So this is equal to minus 2 V1 prime plus 2 okay. So let us now we are in a position to write down the matrix representation. Therefore, matrix representation of T with respect to B prime is given by, see the coefficients of v1 prime and v2 prime. So this is going to be, that will be the column, first column. So minus 1, 1 and minus 2. This is the representation. So we obtained both TB and TB. Now the question that you ask is how let's start with this. Now according to the theory that you have is this. P B prime is in fact P inverse which is equal to, let us write down what it is. This is equal to minus 1, 2, 1, minus 1, that is P inverse. We have already computed this. Minus 1. And this is the TB is 1, 0, 0, 0. And the P is given by 1 to 1. Let us compute this. If you work out the matrix products, then what one gets is the following. If you work out the matrix products, then this is equal to minus 1, 2, 1, minus 1. Now we give the product of these two. To write down the product of these two, now you see that this is essentially 1, 2, 0, 0. And that gives, further multiplying, then you get minus 1 and you get minus 2, then 1, and this is exactly what we computed there. This is equal to B prime. Okay, this is exactly what we computed there. Okay. So I think that is some indication how you actually go through the computation. Now we give a more sophisticated example, or a similar example in a more sophisticated form. Here we straight away work with the R2. Now instead of working with the R3, we are going to work with an abstract space. Let me now work on example 2. Let us choose B to be P2R. Then the dimension of the space V let B where V1 equal to X. Now this is the standard basis that we choose for polynomial spaces. This the polynomial is of degree less than or equal to 2 including 0 polynomial. Okay. Now we choose a second basis . I'm just conforming to the notations that we used in the theory. And let V1 prime defined as 3 minus x plus 3x squared. V2 prime is defined as 2 plus x, and V3 prime now we are looking at the transformation or the linear transformation on V, which we have designated by U in our theory, which maps V1 to V1 prime, V2 to V2 prime, and V3 to V3 prime, and extended by linearity to all vectors in V. So we have U Vi equal to Vi prime. This is the transformation that we are using. Let us write down Vi prime in terms of V1, V2, V3. So we know that V1 prime is equal to 3V1 minus 1 times V2 plus V2 prime is equal to 2V1 plus 1 times V2 plus 0 times V2. V3 prime equal to 2V1 plus that is V1 prime, V2 prime, V3 prime are written as a linear combination of the vectors in the basis V, and that gives you the matrix corresponding to the linear transformation U from Fn cross 1 to Fn cross 1. So let us write down that. Then the matrix P is given by 3, 2, 2, minus 1, 1, 0, 3, 0, 1. In fact, the column 3 minus 1, 3 are the coefficients of V1, V2, V3 in the representation for V1 prime. Similarly, the second column 2, 1, 0 are the coefficients appearing as the coefficients of V1, V2, V3 in the representation for V2 prime. In the same way for third vector also, the third column also. Now P is invertible. This is because P maps carries an ordered basis into another ordered basis according to this rule. Okay. So 1-to-1 map between the two bases. Therefore, P inverse exists, or P defines kind of isomorphism. What a kind of isomorphism is an isomorphism between Fn cross 1 to Fn cross 1. Okay. Now let us take the definition, or let us introduce the operator P. You know that T is completely defined if you can tell what it does on an ordered basis. So let T be given by P1 equal to 5 minus x plus 3x squared, T of x equal to minus 6 plus 4x minus 6x squared minus 6 plus 2x minus square. And this is essentially equivalent to Pv1 equal to 5v1 minus v2 plus 3v3. Pv2 equal to minus 6v1 plus 4v2 minus 6 Pv3 equal to minus 6v1 plus 2v2 minus 4 pi and pi. Please check the sequence. This implies, once again, the matrix representation of T with respect to the ordered basis T B is given by the first column being the coefficients of V1, V2, V3 in the expression for PV1. So it is 5 minus 1, 3. Then minus 6, 4, minus 6. Then you have minus 6, 2, minus 4. So this is 5 minus 6 minus 6. Now our objective is this. We want to get the matrix representation for T in terms of B prime. Not just that, we also want to connect T B prime with T B. So let us do that. So almost repeating the same kind of exercise as we did for V1, V2, V3. We work with B prime, so we will have to work out TB1 prime, TB2 prime, TB3 prime and express it in terms of V1 prime, V2 prime and V3 prime. That will give the matrix of solution for T with respect to B prime. So let me explicitly compute that. So TV1 prime is equal to 3 times TV1 minus TV2 plus 3. I am just using the definition of V1 prime and the definition of this in fact computes to be 3 that is TV1 minus TV2 is minus 6 V1 plus 4 V2 minus 2. Plus 3 times TV3 is minus 6 V1 plus 2 V2 minus 4 and if you simplify the whole thing, this turns out to be simply V1. Therefore, T V1 prime is equal to V1 prime. Likewise, you can compute T V2 prime and show that this is equal to twice V2 prime and compute TV3 prime and show that this is equal to twice V3 prime. This is simple computations. Consequently, the matrix representation for T is just a diagonal form, namely the matrix representation for T with respect to B prime is given by This is of the form 1. So diagonal form. It's accidental in this particular case because took an example which would also serve an example later for diagonalization. Okay. Now you see that we have got both TB and TB prime. How these two are related? We have seen that the relation is given by what you call TB prime is equal to P inverse this is what we have obtained earlier. Let us verify this. In fact, we already have computed P. See, P has been computed as so let us first compute P inverse. So now compute. There are many ways in which you can do it. What I am also saying. One is of course taking the matrix and computing the inverse of this matrix in some form or other, which amounts to exactly what we are doing. So what we do is, see, we have these expressions of V1 prime, V2 prime and V3 prime in terms of V1, V2, V3. Solve them. So consider they are given in the form of linear equations. Now solve for equations in terms of okay, and this, if you compute, I think you should verify this. So let me just give the expressions. This gives the formula computation. V1 equal to V1 equal to minus V1 prime minus V2 prime plus then b2 equal to 2 b1 prime plus 3 and b3 equal to 2 then the matrix representation for U inverse gets computed. That will give you P inverse. So P inverse is then given by which is equal to minus 1 minus 1 3 that's the first column, 2 3 minus 6 2 2 minus 1. Now compute P inverse this is in fact the product of three matrices. Like just give the end product. This is given by this is equal to, in terms of the matrices, you have minus 1, minus 1, 3, 2, 3, minus 6, 2, 2, minus 1. Multiplying the matrix representation for T with respect to B, which is given by 5 minus 1 3 for the first column, minus 6 4 minus 6 for the second column, then minus 6 2 minus 4 for the third column. To be multiplied by P on the right, that is 3 minus 1, 3, 2, 1, 0, 2, 0, 1. And if you go through the computation, then this is equal to minus 1, 2, 2, minus 1, 3, 2, 3, minus 6, minus 1, multiplied by the product of these two matrices. The product of these two matrices work out to be minus 1, 2, 0, 3, and this, if you compute further, gives you 1, 2, 2 along the diagonal. This is equal to 3 prime. Okay. Therefore, P is equal to TB prime. Now this is the final computation. The third example is again in the same setting as polynomials. Please watch. We take dimension of B equal to 3. Now suppose P belongs to B is of the form Px equal to P0 plus P1, where Pi's are this is the general form of the polynomial. Now we consider the formal differentiation operator D defined by D of P Now D is a linear transformation from B to, and of course D belongs to N. Now let us choose two bases B and B prime. Let the ordered base be the standard basis F1, F2, F3, where these are polynomials. F1x is 1, F2x is x, square. These are the definitions. F1, F2, F3 are defined by the standard as chosen as the standard basis. Now we compute D. So D of F1 turns out to be simply 0. D of F2 equal to F1, D of F3 equal to twice F2. Now write down the matrix for this. That is D of F1 equal to 0 times F1 plus 0 times F2 plus 0 times F2. D of F2 equal to 1 times F1 plus 0 times F2. D of F3 equal to 0 times f1 plus 2 times f2 plus 0 times f3. Therefore, the transformation, the matrix representation of D with respect to the ordered basis B is given by 0, 1, 0, 0, 0, 2, 0, 0. What happens is that these coefficients make the first column, these coefficients make the second column, these coefficients make the third column. Now we take another ordered basis. Let G1, G2, G3. These are again polynomials of degree less than or equal to 2. Now we have G1x is taken as 1 itself. G2x we take as t plus x plus t. G3x we take as x plus t whole square, but t is not equal to 0. Some real number which is not equal to 0. Then we have G1x equal to f1x, G2x equal to E of f1x plus T square of f1x plus 2t f2x plus therefore, now we can write also, we have written G1, G2, G3 in terms of f1, f2, f3, from which P can be written as transformation matrix. P between the spaces will be written by 1 P T square 0 1 2 P. This is P. Now P is invertible clearly. Now P inverse works out to be this is easy to compute 1 minus T T square 0 1 minus 2T 0 0 1. What one does is this, from this relation, that is G1 equal to F1. So F1 is equal to G1 itself. Okay. Now you can rewrite this whole thing. So find out F2 in terms of G2, G1 and G2 and G3. So from these expressions, solve for F1, F2, F3 in terms of G1, G2, G3. If you do that, this is what one gets. When I do the computation, maybe we do some inside. I hope there are no mistakes. Let me just compute. Okay. So what I do is, you have F1 is equal to G. Now F2 is equal to G2 minus T G1. Now F3 equal to G3 minus T square F1 2t F2. This, if you replace that, this is, you get G3 minus T square G1 minus 2t. From here G2 and F2, there is a relationship connecting them. So this is equal to G2 minus T G1. And this, if you simplify, this will give you G3 minus 2TG2 plus T square G1. So you have F1 is equal to G1, F2 equal to G2 minus TG1, F3 equal to this. So let us write down that. Therefore, we have and that computes P inverse. Therefore, P inverse is essentially 1, 1, 0, 0 minus T, coefficient of T2 is 1, 0. Then you have T square minus 2t. No. This is P inverse. Now next task is to compute D with respect to the ordered basis B prime. Okay, let us go. You see that, you easily see that D of G1 equal to, now D of G2 computes with G2, because what is it? It's going to be x plus t. You are just differentiating it. So you get 1. Okay? Sorry, D of G2 equal to G1. And D of G3, this is equal to what you get, twice x minus 1. Therefore, this is what you get. So this will be twice. Therefore, D with respect to B prime is going to be given by the matrix 0, 1, 0, 0, 0, 3, 0, 0, 1. Exactly the same matrix as of D with respect to B. I mean, this is just a coincidence. Therefore, you can verify this, compute this. This will be 0, 0, 1. This is P inverse. Then you have the matrix 0, 1, 0, 0, 0, 2, 0. Multiply by this. That is P. P is 1t t square. T square. Go through the computation. 1 minus t, t square, 0, 1 minus 2t, This multiplied by the product of these two. The product of these two is 0. 0, 1 to b, then you have, which will give you the matrix 0, 50, 0, 0, 0, 1. Okay, right. Then you multiply these two, this is what you get. 1, 0, which is equal to that computes the whole thing. And for the second example, I think I'll give you some corrections. So where do we stand now? Okay, let us now take stock of the situation. So that these examples give you some insight into how you compute, go through the process of working on examples. Okay, let us take stock of the situation. Where do we stand? We are interested in the case where the domain and the range are same. That is the first thing. That means we work with t belonging to L. So sum. In this case, we found that, see, t, suppose b and b prime are two ordered bases, then we obtain the following: t b prime is equal to p inverse. Therefore, the matrix representations of t with respect to b prime and t with respect to b are related by a transformation of this kind. And this p is described in terms of how you go from the ordered basis b to b prime. That we have described already. So this is the kind of relationship between these two matrices. Therefore, we shall define A belonging to, let A comma B belonging to and by n matrices over the field F. We say that A is similar to B if there exists an invertible matrix So we say that, see, we have now the following scenario. That is this. So we have got this now the sort of questions that you ask is that are all these matrices always one related to the other as we have prescribed? This is not true, because you see that if A is invertible and B is not invertible, then you cannot have a relation of this kind, because C is always invertible. Okay, and you can easily see that one cannot be related to the identity matrix, cannot be related to the zero matrix. So identity matrix cannot be related to any other non-identity matrix more generally. So see that if you look at this as a relation, suppose we write A is related to B if A and B are similar. Then we observe that not remark, not every matrix related to every other matrix in for example I the identity is related to only itself. So also zero matrix is related to only itself. Therefore, there are, given a matrix, there is a whole class of matrices which are related to it, and a whole class of matrices which are not related to it. Now, what kind of relation is it? This is what we ask. We note that this relation between matrices is an equivalence relation. That is, A is related to A related to B implies B is related to A is related to B, and B is related to A is related to B, B is related to D implies A is related to, I don't mean D diagonal. I don't mean D diagonal. This is easy to prove. I leave that as a little exercise for you. Okay, so prove this. What is the consequence? The consequence of an equivalence relation is that it partitions. Therefore, it partitions M into equivalence classes. What do you mean by that? This is broken up into disjoint class of sets whose union is the whole of this, such that in every block the matrices are mutually related. If you pick a matrix from one block and another one from another block, they are never related. So this is the situation that you have. Okay. So in short, what we have proved is that if you take a bounded linear transformation or just a linear transformation on V, so we are talking about finite dimensional spaces, on V, it has several matrix representations, and the relation between all these matrix representations is that they are related to one another in the sense of this equivalence relation that we have defined. Okay? In short, what you have is that for any transformation T, linear transformation T on V, you have a plenty of choices of representations in terms of matrices which are related to one another. Now, this is the situation. So let us see what is the consequence of this. The consequence of this, or the advantage of this, is the following. Let me first talk about the disadvantage. The disadvantage is that for a given linear transformation on V, except in some cases like the identity operator or zero operator, you do not have a unique choice of a representing matrix. The advantage that you have is that for every linear transformation other than for I and 0, you have plenty of choice for representing it. There are several matrices which represent the same linear transformation related to one another. Therefore, the advantage, we exploit the advantage by exercising our option, namely choosing a reasonably simple representative matrix. Okay? So this is the central problem that we encounter. So how to choose separation for given t belonging to from among all available representations. This is the central problem that we will be encountering now. We will explore this problem. First of all, we are still vague about what we mean by a simple representation. Okay, so we have to make that clear. All that we observe at this stage is that there is a problem of plenty, and we have to choose one of them. We have to fix the criteria. What is going to be the most advantageous choice that you can make. We will explore this in the coming lectures. Thank you very much.